Hello everyone, here is Orillusion. Welcome back to WebGPU fundamental tutorials. Last week we learned WebGPU 3D transformation, and we know how to dynamically draw in a graph using the vertex information and BindGroup. And today we'll learn how to draw multiple objects in the scene. Let's briefly review the knowledge about BindGroup. Let's look into this figure. We pass the vertex information directly into the vertex shader through the vertex buffer. And we also create a MVP matrix to do the 3D transformation in JavaScript. And then we pass it into the vertex shader through the set BindGroup. Finally, we multiply the MVP matrix with the vertex coordinates in the vertex shader. So except for the MVP matrix, we combine the data resources such as color, texture, and configuration into groups. And then by setting a different bind group to control the data switching between multiple objects. So let's practice now. We will learn 4 different ways to bind resources. And the demo will be placed in our GitHub repo. Let's first look into this cube TS. We added another rotating cube based on the previous tutorial, with a different combination of resources. In the last video, we created an MVP buffer for an object, and also created a band group to bind the MVP buffer. And finally, in render pass, we pass this MVP buffer into vertex shader through the set band group. So for drawing 2 or more objects, the easiest way is to repeat this operation several times. In this init pipeline, we can create 2 MVP buffers, and they are with the same size. And then we created 2 groups, and the structure is actually exactly the same. And finally, we return them. And here we simulate the position, rotation, and the scale of these 2 objects. We calculate their corresponding MVP matrices separately in the loop, and then write it into the corresponding MVP buffer. We package this MVP matrix calculation function into the getMVP matrix function. And let's come back to the draw function. Because these 2 cubes using the same vertex data, so we just need to set the vertex buffer once, then set the band group corresponding to each object, and then repeat the draw twice. Because the final state of the object in the vertex shader is only related to the input vertex data and the MVP matrix. So when we reset a different bind group, that is equivalent to switching the input of the different MVP matrix. In some scenario, if the model is different, then we can switch different vertex buffer, such as vertex buffer 1 and the vertex buffer 2. That is also same for the pipeline. We can also switch from pipeline 1 to pipeline 2. But here we need to make note. Although the modern graphics API has been optimized a lot, compared with the global state machine of WebGL, it has been greatly improved. But switching between pipelines for the configuration or data, it is still a very large overhead. And the most expensive one is set pipeline. Of course, it involves switching the entire vertex shader and fragment shader. That is why we try to replicate pipelines as much as possible. If each object in the scene is independent, so you have to switch the entire pipeline every time you draw, then the rendering efficiency will be greatly reduced. The second expensive is set vertex buffer. Because set vertex buffer will identify and convert the vertex data according to the pipeline configuration. The last expensive one is set band group. Because the band group itself is an external and global variable, so there is no effect on the configuration of the pipelines. It's just a copy or a repoint of the memory pointer. This is a very efficient operation. So when we develop WebGPU applications, we must consider the penalty of these APIs. In principle, switching between the states of GPUs should be minimized during the drawing process. So when we draw multiple objects, switching band group should be most preferred, and then vertex buffer, and finally switch the pipeline. So in practice, when we draw a pipeline, it's best to draw all the objects related to this pipeline first and then switch to the next one. Don't switch back and forth frequently. And in the same way, when we're drawing a model vertex, we try to draw all related objects firstly and then switch to the next vertex model. And that is the same for the buffer. So let's have a look into the second demo, how to optimize the BindGroup. In this demo, we didn't create two MVP buffers. Instead, we use a larger buffer to store two 4x4 matrices. We still need to create two groups, but the difference is that they are bounded to the same MVP buffer. We'll set different offset and size to read the contents of the corresponding buffer. So when we execute send BindGroup in render pass, GPU doesn't need to read the MVP buffer address. We just need to move the pointer according to the different offsets in the group. Compared to the first demo, we improved efficiency and the speed. Let's do a simple test. We just add a loop here and check the difference between the frame rates. The frame rate difference in these two examples will be caused by the different losses of the send BindGroup. So in the first demo, it shows the frame rate is about 34, but the second one is 36. It is faster, but not very obvious. Because in the first demo, we just used two different buffers here. The randomness of memory distribution is not very large. But if we set 200 and 1000 buffers, then it will be very obvious. This kind of continuous memory operation actually works just in the CPU as well. Especially for JavaScript, the promotion is very obvious. We may talk about this later. And let's look into this send BindGroup. People may notice here, why do we set the size here to be 256 by 2? That is actually required by WebGPU. When we bind multiple groups in the same buffer, we have to leave enough alignment space between each group. We can query the specific value through the limits in this adapter. The minimum limit is 256. So although a 4x4 matrix is only 64 bytes, but we need to set 256 bytes for the alignment. But we don't have to leave enough space for the last group. So actually we can set 256 plus 64. But for convenience, we just write a multiple of 256 here. So the first group offset will be 0 and the second offset is 256. Let's briefly summarize the difference between the first demo and the second demo. We combine multiple buffers into one contiguous buffer. Although the cost and complexity of creating groups have not changed, and we just point to the different locations in the same buffer. It is much more efficient when switching groups. However, because of the limitation of WebGPU alignment, we actually increase the memory size. If it is a 1x4 color data, then we'll consume 16 times of the video memory. Besides, when JavaScript writes the GPU data, we also need to do this 256 alignment. Now let's move to the third demo. We also use a contiguous buffer to store the MVP matrix and also do the 256 alignment, but this time we just need to create one group, and we don't need to set offset. And we'll use a feature of group, which is dynamic offset. This feature is not enabled by default, so we manually create a group layout and set the buffer information, as well as its buffer type. It is uniform or storage, and wider to support dynamic offset. Correspondingly, we also need to change the default group configuration of the pipeline. We also need to dynamically create a pipeline layout. So when we call the set BindGroup in the render pass, we can set group uniformly. Here we need to add an array parameter, which is used to dynamically set the offset between the data. So the first object, the offset is 0, and the second offset is 256. The difference between this demo and the second demo is that we have to specify the offset of the group in advance. And we can dynamically set the offset in the render parse. Makes the group management simpler, and we reduce the overhead of creating groups, and the operation is more flexible. But we need to set the layout of the group and pipeline. And the overhead of buffer switching is no difference between the second example. So the performance is good. However, we still need to follow the 256-byte alignment. Let's do a simple test here. We set a loop for 200,000 times and then test the performance of set BindGroup. We found that the frame rate is only 18 frames. It's almost just half of the previous one. If we set a unit 32 array for the offset, then it will raise the frame rate into 30. But it's not as good as the first two demos. And why is that? Actually, the consumption is on this JavaScript API. So although for GPU, the dynamic offset method is similar performance with the ordinary group switching, and maybe even faster, but for this API, the JavaScript consumes more on CPU side, so the overall performance is reduced. So advantages of this third demo is mainly on the reducing the overhead of creating groups. So for some other scenarios, if we don't need to create new groups, then this method may not be good. Can we achieve even better performance? Let's look into the fourth demo. In this demo, we have 100 cubes, but we just create one MVP buffer and one group. But unlike the demo 3, this MVP buffer does not need to use the 256 alignment. We create a size according to the number of matrices. We set this buffer to be a storage buffer, because the uniform buffer only supports 64 kilobytes. That is, 1,000 matrices can be stored. However, the storage buffer can apply for a size of 128 megabytes. We can store 2 million matrices. We don't need to set offset for the corresponding groups. And MVP matrix calculation is no different from before. We just add a loop here to automatically generate the cubes according to the number. In each frame, we iterate all the objects in the scene and then dynamically change their rotation and create the corresponding MVP matrix, and then write them into a big MVP buffer, but it is not 256 aligned. Let's look into the code in Draw. We just set BindGroup one time, but we add a second parameter into Draw function. Num is corresponding to the numbers of the objects in the scene. The first parameter is how many parallel threads to open to execute the vertex shader. And if we say the number of the first parameter is regarded as one group, so the second parameter means how many groups we want to start at the same time. So for this demo, the vertex count of the cube is 36. And if we say the second parameter is 100, then that means we start 100 groups to run at the same time. And if we draw 100 times through a loop, then we first draw the vertex of the first object, and then we do the color and assembly, and then we start a second cube, and then do the coloring and assembly and so on. Although for a single object, the GPU will draw multiple threads in parallel, but for the whole scene, it is a single-threaded. In fact, we didn't utilize the parallel compatibility of GPU in this form. But for instance draw, we draw 100 cubes vertices together at first, and then we do the drawing for the 100 objects in the same time. So it is much more efficiency. But if this 100 cubes run in parallel, then how do we switch the resources? Let's look into the shader code. In the first three demo, the MVP matrix is passed into vertex shader, which is a 4x4 matrix, and the content of the matrix is actually managed by JavaScript. But in this demo, we passed the entire MVP buffer for all the cubes directly into the vertex shader. So here we need to change into an array of mat 4x4, which means the shader will automatically split the large storage buffer according to the size of mat 4x4. So how do we get an individual MVP matrix in the shader? And we introduced in the triangle vertex shader. Apart from some external vertex data, the vertex shader can also have some internal parameters. For example, the add built-in vertex index. So similarly, in this demo, we can create an internal parameter built-in instance index. It just indicates which set of instances that we are currently running, i.e. which cube. We can just operate it like a normal array. And we can access the corresponding MVP matrix content in the large MVP matrix through the index. To sum up, the biggest advantage of the instance draw form is that the rendering pipeline is very efficient, and we maximum the parallelism and compatibility of the GPU. The management of resources like the switching between the buffer and the group, we put it into the GPU, i.e. the shader, to do this. So in JavaScript, we don't have to create multiple buffer or groups. So we eliminate the overhead of these APIs. We don't have to do the offset, so we have advantages in the memory. In terms of rate performance of the buffer, the second and the third demo are also continuous buffers, but it has to do the 256 bytes alignment. However, in this demo, we just need to move as long as the data is. So it will be faster. From the perspective of API calls, if draw function has been called multiple times because of the for loop, so the overhead for JavaScript and native APIs are very large. Another advantage on the performance is how the JavaScript update GPU buffer. In the first three demos, the GPU buffer was written independently according to the number of objects. Let's test the performance of a for loop writing. Okay, we see that it takes almost 20 milliseconds to write each of 1 million boxes, and the frame rate dropped into 10. In another way, if we create an array of the same size in JavaScript and write data into this array first, and then finally we can write the content of the JavaScript into the MVP buffer, and let's see the difference. And the running time is shortened into 8 to 10 milliseconds, and the frame rate is nearly full. That is to say, we need to minimize the time of exchanging data between CPU and GPU to reduce the communication costs. So ideally, all data should be prepared in JavaScript or CPU first and then read into GPU all at once. And of course, WebGPU has other forms of API to optimize this situation. We'll introduce this later. We can also find another advantage of instance buffer method is unlike the second and third demos. Because of the offset, it is 4 times and 16 times larger than this fourth method. So until now, it seems that the instance buffer method is perfect. Are there any downsides? As I just said, because of this parallel relationship, all instances must be using the same set of vertex data and group information. But there is no way to switch the vertex information. So we can generally only use the objects with the same vertex data. In this way, instance draw method will not work for some other common scenarios. But of course, in practice, we combine different methods to optimize the overall performance. Finally, let's summarize these 4 different managed resources ways. Firstly, let's look into the code complexity. In the first demo, although we need to create multiple buffers and groups, but actually it is the easiest. The second method, we use a continuous buffer. It might be hard for some JavaScript developers because it doesn't need to consider the offsites. So both read and write operations are difficult. As for the third method, it is the most difficult. We need to create the custom various layouts, and we also made changes to the same BindGroup API. For the last method, the JavaScript code is very simple because we put all the logic into the shader, so it will be difficult for the vertex shader writing. In terms of flexibility, it mainly refers to the flexibility of control of the buffer. The first method is good, and second and third are similarly. But for the same vertex information, the fourth method is the best. For read speed, we just tested. The first method is the slowest, and the second and third with continuous buffer are much faster. But run dynamic offsite in JavaScript will be slower. So the third method will be good for the scenarios where groups need to be created dynamically. And the fourth method is the best, but it just works for switching between the same models. For write speeds, it's actually similar to the read speed. These grid buffers will be much slower because of the time while moving the memory pointer, and the extra overhead of establishing data channels between JavaScript and GPU. Latter 3 methods, because they are using the continuous buffer, so it will be very fast. But because of the extra data size due to the offsite, the second and third method will be relatively slow. In terms of memory, the first method using the discrete buffer, so there is no redundant data itself. So n objects just need n buffers, and we just need to create n groups. And for the second and third method, we need to according to the offset limitation. So we consume more memory. In metrics like 4x4 size, we actually use 4 times memory. And for a 1x4 color data, we'll consume 16 times memory capacity. And in dynamic offset method, we only need to create one group, so this part of the cost is fine. For the instance method, it is the most efficient in terms of memory, no matter on the buffer and the group. So these 4 different resources management methods have their own advantages and disadvantages. We need to design our resources management approach according to a specific scenario. But in general, we need to use continuous buffers as much as possible and combine these 4 methods together to achieve a balance between the performance and efficiency. We will gradually introduce the optimization practice in the relevant scenarios in the future. Okay, that's all for today. In the next video, we'll learn the basic of textures and use pictures and videos to enrich the display of our 3D scenes. Please feel free to leave any comments or feedbacks below our video, and welcome to subscribe our channel. I'll see you next time.